Hello and welcome to another video. Today we're going to be working on interleaving string. And in this problem you're given two strings, or three strings, and you want to find out if S3 is formed by an interleaving of S1 and S2. Interleaving means there's a configuration where S and T are divided into N, and you have substrings. So essentially what it's saying is, can you break down these two strings to form, like, it's kind of like Scrabble, right? Like you have these letters and you have these letters. Can you combine them to make these letters? Pretty much. But also they have to be in the right order, right? So like let's say your string is, let's say your two strings are like A, B, B, B. And then you also have another A, B, B, B. You can't make something like B, 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 A, right? Just because you have the letters, like the order of the letters you use has to be maintained, as you can see in the picture. So this picture shows that like this is the first word, this is the second word. And you can see the letters of the first word have to be used in order, and the letters of the second word have to be used in order, right? Otherwise, this would be a really easy problem. And so they're kind of showing how to do that in this example. So for this first example, you're splitting A, B, C, B, and then so on, and then you are interleaving them. And for the second one, you can't. So essentially, we're going to go through this, and if you've done the problem of the day for this month, there are a lot of problems like this. It's going to be a DP problem where you have two choices, either to use one or the other. And so that's pretty much what it's going to be broken down into. So let's actually break it down into right away DP, because that's what it's going to be. So for DP, we need a couple things. We need we need arguments. We need base case, and we need recursive case. Okay. But yeah, essentially at each point, like you're going to be at an index for both of these, and you're going to say, like, let's say you're over here. You're gonna have two choices. You can either use this or you can use this. You can't like skip, right? And then you need to build up this whole word essentially. Oops. You need to build up this whole word. So at every point you're gonna have a choice. Which one do I use? And then where does the letter corresponds to? Well, that's pretty easy. You can just get that index by adding up the first two. So for example, let's say you're at this index. This is index 1, and let's say you're at this index. This is index 2. Well, if you think about it, you've used 3 letters so far, so you'd be on the 4th letter. So that'd be this index here. So it'd be index 3. You just add them up. So if you add them up, that would be the index where you are in the word. Okay, so you only need 2 variables. You can technically pass in 3 because for every I1 and I2, I3 will always be the same, right? Whenever this is 1 and this is 2, then that third index will always be 3. So you can pass it in. It's not going to like add more states because it will always be the same. But regardless, let's go through the arguments. So the arguments here is we are going to have I1 for the index of the first string, I2 the index of the second string. Okay, well, what about some base cases? So what like issues can we run into? Well, let's say we are out of bounds in one of them, right? Like we just say we went through this whole first word and we're out of bounds. So you could technically, if you wanted to, and it might even be a shortcut, you could say like, okay, I'm out of bounds on the first word. I am at some location on the second word, call it here. And I have 4 letters left in this word. So I could just say like, let's just check this to equal the rest of the word. Like I don't need to do DP, right? I can just check it. And if it's that, then we're good. You could totally do that. I'm not going to do it in my solution, but you could totally do that. So I'm not going to have that be one of the base cases, but you totally can, where you're just out of bounds on one word. You just check, is the rest of my second word equal to the rest of the, whatever word you're trying to build. Okay. What about if you're just out of bounds in general? Like you're out of bounds here, and you're out of bounds here, and you're out of bounds here. Well, that is the case where we have a solution. So that is one we will use. Let's add that in. So out of bounds on every word equals true. We have a success. Okay. What other base case do we have? So there is another thing we do have to check, and it's not going to be part of the recursion, but let's say this is like link 3, and this is link 4, and this is like link 15. Well, obviously you can't make this if these 2 links have to add up to this link. So that is one thing we're going to check outside of the recursion, but that is going to be a base case. So we will add that in, and we will check that outside of it. Okay. So length of 1 plus length of 2 does not equal length of the third word. And what do we do there? Pretty straightforward. We will return false. And those are pretty much our only two base cases. And then the other base case we're going to have, it's not going to be a base case. We're going to try the recursive cases. And if either, oh yeah, there's one more base case, right? So there's the cache case. So obviously if it's in the cache, then we're going to be returning true. But other than that, we aren't going to be returning anything else. So what we are going to do is we are going to try the recursive cases. And if neither of those works, then we will return false. But let's also think about also our cache here. And I would recommend this. So in this problem, we are asked to return true if something happens. So in any problem where you're asked like return true if something's possible, this kind of DB problem, you don't need to use a cache. You can just use a set, because everything in the set will be false. And if you ever get a true value, like if you ever get to the base case, then you're done. You can just recurse all the way out and return true. So we're not asking for like the number of possible combinations or anything. We're just asked like, is this possible? So in that case, we're going to use a set. And if it's in our set, that means it's going to be false. So cache, going to be false if it's in there. Okay, so what about our recursive case, right? So for the recursive case, what can we possibly do? Well, let's look at this picture. So let's say we are on some indices, like let's say we are on this index and this index. Well, there's still only two things that can happen, right? We have to find the corresponding index on the big string. And then we have to ask ourselves, like, do these match? And if they do, let's try to use this. Right? That's one case. And then the other case is, do these match? And if they do, let's try to use this, right? And we can either try to use one letter or the other, and we can only use them if they match. So that's pretty straightforward. So we'll just say if the letter of first word matches or equals letter of main word, try to use it. If success, return true. And then the same thing for the second one. So if the letter of the second word equals letter of main word, try to use it. If success, return true. And if neither of these happens, like if we tried both letters and neither of them failed, what do we do? Well, it's pretty straightforward. We just cache it and return false. And so that's pretty much it to this problem. Like you're essentially at every index, you're just checking, is my letter equal to the letter of the main word? Like, is it even a possibility? Because, for example, if I need to get a B here, and this is A, obviously I can't use that. And if I need to get a B here, and this is D, obviously I can't use that. So if I can't use either of the letters, then obviously in this state, that would be false. But if you can use a letter, then you just up the index of whatever one you use, and you keep going until you're finally out of bounds on both. And that's pretty much it. And so let's actually look at the solution in LeetCode for the recursive case. Let's go over it. So here it is. And we just have if the length of S3 does not equal the length of S2 and S1 are obviously, or there's no way you can have that. Then we have our visited set, and then we have our two indices. And then if we are out of bounds on both, we will return true. If they're both invisited, then let's return false. And otherwise, we calculate the index for that third, this big string, and we just say, okay, well, if I1 is in bounds, because that's the other thing, you can be out of bounds on one of these. Like, let's say you're done with this word, but you're still in this word. So if you're done with this word, you can't use a letter from this word. So you have to make sure, like, you're in bounds. If you're in bounds and your letter is valid, and your DP recursive state returns true, right? So let's say you use a letter from the first word, you would just increment that index. I2 would stay the same. If this is true, then you would return true. Similarly, exactly the same thing for the second word. If that's true, you return true. Otherwise, you just add it to this, and it's going to be always false. So pretty straightforward. Like anything in our cache is always false, and then we just call that on the base case, and we just return that. Okay, so that's one way to do it. Now, another way to do it, and I'm going to go over this, is, and if you've seen any of my other problems, it's a dynamic programming solution where we do bottom-up DP. And so we're going to have to like figure out these states essentially. So let's just draw this out. And what we're actually going to do is we are going to draw, so this is 5 by 5. We're actually going to draw a 6 by 6 because we need that empty box as well. So let's do that. So let's draw a 6 by 6. Basically, as always, my lines are the worst. So 3, 4, 5, 6. Then obviously they're uneven, otherwise it wouldn't be one of my videos. So 3, 4, 5, 6. Okay, and now what we're going to do is we're going to draw the letters. So essentially, let's say this first word is AABCC. We'll call this like, I don't know. It doesn't really matter which word you put where, but let's just say we put this AABCC here, for example. And then you have DBBCA. And essentially this last like row and column represents us being out of bounds. So we'll go over that. So now we need to also draw, so this is DBBCA. Now we need to also draw ideally the indices for each of these. So let's do that as well. So this is like index 0, index 1, index 2, index 3, index 4. Same thing here. Index 0, index 1, index 2, index 3, index 4. And this represents out of bounds. So like, for example, the state, let's just say here, like what does this represent? This represents we've used all of these letters and all of these letters. And let's actually write our string to make it easier. So let's say our string is A, D, B, B, C, B, C, A, C. I'm not going to index it, but you can. But essentially, it's kind of the same thing. Like, for example, if you are here, this would be index 8. So it would be like, I guess we should maybe index it, right? Just to make it a little bit easier on us. I'm not going to fill out this whole thing either, but I'm just going to show you like the first few rows, and then we are going to like figure out what to do from there. 6, 7, 8, 9. Okay. And so what's going to happen here is this represents we are done. Like we're done with both of these words and we're out of bounds here. And so this is our base case, right? So this is true. But what about like these and these? So what does this bottom row represent? Well, this bottom row represents we're out of bounds on this word, but we still have letters here. So for example, this right here represents we're on this letter here, right? It's both these indices added together. So I guess this is actually, yeah. So this is, so let me actually draw that. So this is 5 and 5. Okay. So that represents, yeah. So this square here represents index 9, and we are out of bounds on this word, and then we are on letter C on this word. So is that possible? Yes, it is. So in order for this to be possible, two things have to happen. A, the letter has to match with whatever you're doing, and in this case, this letter has to match this letter, and this one, like one of the states after it. So in this case, like what happens when we use a C? So if we use a C, we'll be on this state. So these have to match, and the state after it has to be true. So in that case, that is both true. Okay. What about this state here? So this state here is we are on this. We are on index 8, and this is this A, but we need a C. So this is representing this, and we're saying, okay, can we use this C? Well, no, obviously we can't, because the A does not equal a C. So this is false. And now remember, for all of this bottom row, this letter, like this letter, has to equal the letter over here, and the state after it has to be true. So obviously, once this is false, the rest of this is false. And let's do the column here. So what does this column represent? So this column represents we are out of bounds on this top word now. And so in this case, for example, this letter 9 has to equal A. Does it equal A? No, it does not. So this is false. And then same thing, for all these, the letter has to match. So like this C has to match whatever it is up here, and the state below it has to be true. It has to be both. And if you think about it, that makes sense, right? It's like, can I use this letter? And if I do, I'm in this state. So this state also has to be true. Both of those have to happen. The state you go to has to be true, and the letters have to match, right? As in a recursive solution, if you would go back, the letters have to match, and the state after has to be true. So it's the same thing here. So now that this one thing is false, this whole thing is false. Okay. And now let's maybe do like one more row, and let's show our simplification. Okay, so here, once again, we are going to look at a couple things. So here we have a C and we have an A. Well, this is index 8, so here's the index. So there's two things we can do. Like, let's say we use the C. If we use this C, where will we be? Well, if you use the C, we'll be over here. So obviously we can't use the C because that would be false, but we could try using the A. So if we use the A, it will be down here. Can we use the A? Do the letters match? Yes, they do. So this would be true. Okay, now let's keep going. So here we have a C and an A. We're at index 7. Now, we cannot use the A because if we use the A, we'll go down, it will be false. Can we use the C? Yes, we can because the C doesn't match. So this will be true. Now here, we have a B and an A, and we're at index 6. We cannot use the A because this is false. So here we can't use the A ever. So can we use the B? Yes, we can. So true. Now here, can we use the A? And if you look, this is index 5. So we can't use the A or the A, so this is false, right? Because this is corresponding to this index, and neither the A or the A corresponds. And here, once again, it's A, and this is at index 4, and this is false. Let's do maybe one more row and just call it there. Okay, so here we have index 7, and we have a C or a C. So obviously we can use a C, but we can't go this way because that would be false, but we can go this way. So that works. So this is true. Either one of these has to work. Like one of these letters has to match and the thing has to be true here, or this letter has to match and the thing has to be true. Either one of those. Okay, now we are on index 6. Can we use a C? Well, no, because the letter doesn't match. Okay. Now we're on index 5. Can we use a B or a C? We can use a C. So if we use a C, we will go down, and that works. So this is true. Hopefully I'm doing this right, but that's essentially, maybe I screwed up one of these, I'm not sure, but that's essentially what you're doing. You're just checking, does my letter match? And if I use the letter, like if I use this C, I go down, and if I use this A, then I go right, and so on. Okay, so if I use the C here, index 4, well, first of all, we have a B, right, at index 3 plus 1, so all of these are false because the letter's just different. And then at index 3, we also have a B, so this is false. So you keep doing this, and then once you get a thing here, this represents starting at this index. And then if this is true, well, whatever this is, you just return, right? And this is going to be the same complexity as the recursive solution. But notice one thing. Every single state depends on two things, right? Like, well, this state depends on, yes, the letters have to match, but it also depends on this state and the one below it. So this state and the one below it, and so on. Every state depends on the one below it and the one to the right. And so whenever you have that case in dynamic programming, just like in, like let's 5 other problems of the month this month, you can space optimize this. So you can space optimize it by only keeping track of one row. And let's just do one row here to do that. So we're going to start off with this bottom row here. Okay. And so we're going to start off with this bottom row. And we're just going to do maybe like 2 rows and kind of show how to build it. And then we're not going to do the whole thing, but we're going to do the bottom row. So 1, 2, 3, 4, 5, 6. So remember, this bottom value in this bottom row, it does need to be true. And now where do we go from here, right? Like how do we get these values? Well, what we can just figure out, like we can still keep these indices. We just need the bottom row. So we can say like, oh, we're in the bottom row. So for the bottom row, what has to happen? Well, the value has to match of this array or this string, and the value to the right has to be true. And so let's look at this character here, which would be this. So, and like I said, we know this index because we can still loop. We're just going to only maintain one array. So here we'll say like, okay, does this C match? This is at 9. Yes, it does. And is the value to the right true? Yes, it is. Okay. Well, what about here? Does this C match to index 8? No, it does not. So this is false. So remember, in this, you can only go, so now we would just go right and we'd make all these false. Right? So this row matches this row now. Right? Like this row matches this row. Okay. Well, how do we do this row now? And so essentially how we do this row is we will just say, okay, let's just keep the row we have. Let's just keep that because that represents going down, right? Like these numbers represent going down. So then we can just calculate that first. So we can say like, okay, in order to go down, what has to be true? Like in order for going down to be true, what has to be true? Well, the letters have to match going down. So this letter has to match whatever index we are on, right? Because this would be going down from this row. Like we're on this row right now. So like, for example, A has to be at index 9. Is it here? Well, no. So if this is false, so we're essentially going to do, okay, does the letter match? And this is true. Well, the letter doesn't match, so it's false. Okay, what about for this one? Right? So here we still have the letter A. Does that match? Yes. And then going down is true. So it's true and true, right? So this letter does match. and going down is true, as you can see, and we're going to do it in place, right? So the letter does match, and going down is this value here. So we're just going to say, if the letter here matches and this is true, then this is true. Okay. What about here? Does the letter match? So this is at index 7, and it needs to be an A. No, it does not, so that's false. Okay. What about index 6? It needs to be a B, and the one below it has to be true. Well, so anything, all these falses will remain falses because essentially the letter has to match and this value has to be true. And so whenever the ones that are false will always be false, and then the ones that are true will either stay true or turn to false. So now essentially we have this part, and now this is just representing like trying to go down. Well, we can try to go down, but we can also try to go right, right? And so to go right, two things have to happen. The letter has to match, and the thing to the right has to be true. And now remember that for these, you like either one of these has to be true, right? So for this has to be true or this has to be true. And we just check the bottom part. So anything that's true, now that we check the bottom, will stay true because it's one or the other. But anything that's false can be true, but it might not be. Like it can possibly turn to true because we're checking the right side now, essentially. And so for the right side, like for this letter that will correspond to this letter, where you can say like, okay, like this is obviously out of bounds. So for the out of bounds, this will stay the same. But for this, we can say like, okay, does this letter match? So what is this letter to go right? This letter has to be a C at index 7. Yes, it does. Okay, and the value to the right has to be true. Yes, it is. Okay, well, if both of those are true, then we can turn this into a true. Okay, what about this letter here that corresponds to 1, 2, 3, corresponds to this value? Okay, so this value has to be a B. Well, yes, it is. Is the value to the right a true? Right, like this letter is a B because we are going right. So if we're going right, we're using this top word. Is the letter to the right true? Yes, it is, right? This is true. So both of those criteria pass. So that's true. Okay. What about this one? So that corresponds to this. So this is the letter A. It has to be at index 5. That's the letter C, so that doesn't work. Okay, what about this one? This is the letter A, and it has to be at index 4, and that's also not true. So now this is this. And you keep doing that again. So for like this state, you would say like, okay, here's my bottom states. I need the letter to match and for these to be true. For this bottom part to be true, and it's either the bottom or the right has to be true, right? So we can write that down. So at every state, either the bottom and the letter. So either, I guess we can write it like this. 1, the letter on the row has to match the index in the string, and going down has to be true, or the letter on the column has to match the index on the string, or in the string, and going right has to be true. So it's like this or this, but then either both of these are two different conditions. So it's like, so one is like something and something, and this is something and something as well, and then you or between them. And that's essentially what you do, and you just keep building up and building up and building up until you're finally representing this row 0, and then you just return this first value here. So I'm not going to build up the whole thing, but that's essentially what it works. And it is kind of like hard to follow as well, because you have to like look like which letter am I using? Am I going right? You know, it's a little bit tougher than coin change, I feel like, to kind of see the states. But it's basically just like a tougher, like once you visualize what's going on, that's why I think this drawing this is really useful, then you can kind of understand what's going on. And it's literally the same as coin change, going down a maze, like all those, any problem where you're going right and down, it's all the same. Just one small change. Okay, so let's look at the code there. And so we have a few more checks here, because you do have some edge cases that I found, and here they are. So same check here. If the length of the third string does not equal the length of the first one and the second, obviously we would return false. But there's two other edge cases. So if one of these strings can actually be empty, and so if they're empty, this gets kind of screwed up. So if you think about it, like if S1 is empty, then it's pretty easy. You just compare S2 to S3, right? Because you can't use anything in S1. And the same for the other one. If S2 is empty, we're just going to compare. Because this will break this DP, because then our DP will like have length 1 when there is no string. But other than that, it's just, I'm only showing the bottom-up DP. I don't have like the two-state bottom-up DP. I just did the space optimized one. Just because I've done, and I will link up like 5 other problems that have literally this pretty much exact same algorithm that I've done this month. So if you want to look into that more, if you want more problems like that, I'll definitely link some more. But yeah, essentially you're just looping through your strings and you're saying this is the case where you're actually at your bottom right index. And so if your bottom right index, you want to leave that as true. And then these are the 2 cases where you're out of bounds on one of the strings. So if you're out of bounds on one of the strings, you only have to check one direction. And then this is the case where you're on anywhere else. So it's essentially like an and with an or, and this is like the 1 or the 2 essentially. Pretty much that. And we can test it as well. And it should be reasonably efficient. Yeah, so you can see it's reasonably efficient. And like I said, I will include the code, and I will also include links to a bunch of other problems. I do think this one's a little bit tougher to visualize for bottom-up DP. Like I think recursively it's pretty easy, but for bottom-up DP it's definitely kind of hard to understand what's going on. So I would maybe recommend doing some easier ones like traveling down in a maze, get that one space optimized, and then build up to something like this. But yeah, it's going to be, oh yeah, let me actually go through one more thing. So let's go through the time and space here. Forgot about that. Okay, so for this recursive and for this bottom-up DP, essentially your number of states is the length of both strings combined. So it's going to be like S1 times S2, right? Because that's how many states you have, and then in every state you either go down or you go right. So that this is like every single DP should be of 1. So essentially time is, you know, we can call that like m by n or whatever you want if that's your strings. And then the only difference is that the recursive solution is m by n space, and then the optimized DP solution is either O of m or O of n space. You could make like, maybe you could argue, you could make it like a slight optimization. You can say like, let's just make sure the array is like the smaller string if you wanted to, like that would be totally fine. But either way, it's going to be roughly the same. So we'll just call that O of n for the space optimized one. But yeah, like let's say one string is like 100 characters, one string is 2 characters. You could technically say like, if you wanted to, I mean, I guess we could even do that here. So we can say like, so which, like, let's look at which string we're using to make the array. So here we're using S1 to make the array. So we could say like, if length S1 is greater than length S2, we can just swap them, right? And we can just say like, okay, well, let's just say S2, S1, we can like swap them basically. Should work still, I think. Let's give that a go. Yeah, so you can see it's like a lot more space optimized, but the time is going to be the same. But yeah, roughly that. You know, I'll paste the code and everything as usual. So yeah, hopefully you liked this problem. And if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.